Hello everyone, my name is Tiffany, and today we're going to start with the transform from scratch exercise. And previously we stopped at the cross entropy loss, which is calculating the loss log probability for tokens. And you can see that if it's completely random with uniform distribution, the loss is 10. But uh, with the model running, then now the loss is 4. So it's working. And now we're going to start with training a transformer, create model, training argument, create data, tokenized data sets, and then a training loop. So I'm just gonna write it down, write it down, uh, without testing it. And the truth is, I've already done this test multiple times and making sure that it's correct. So this time I'm gonna do it without AI helping me, while explaining the step-by-step process. So now we're gonna train a transformer and we're gonna do the training step. So especially in the first chapter last week in the fundamental section, you've learned what is backpropagation, what is gradient descent. So it's very similar to that. So we start with tokens, and batch is a dictionary, right? You put in the key and you put it in a device. After that, you calculate the logits, which is the self.model tokens right here, model tokens. And after calculating the logits, you calculate the loss. And using the previous stuff to get log prob, which is the previous function, you input the tokens and then the logits. This is logits and then tokens. Logits and then tokens. You start with 0. It's logits and then tokens, and then you calculate the mean loss across all the sequences. So remember, as a transformer, when you input 100 sequences, when you input a sequence of 100 tokens, it produces 100 logits. And what makes a transformer great is this parallelization that makes computation very, very quick. And you calculate all the average of those loss, and then you go through the backpropagation, which is loss dot backward, and then you update the gradient descent, which is optimizer dot. No, the zero grad is later. Before that is self dot optimizer dot. What is gradient descent? Is it? Yeah, it's just step. So self dot optimizer step, which is the gradient descent process, and then the loss dot backward is the backpropagation process that calculates the gradients. And then self-optimizer is when you actually update the gradients and then you remove the old gradients. Afterwards, self.step plus equals 1 to calculate, oh, we've done one loop of training, and then you want to log it in weights and biases using 1b.log. 1b.log. The syntax is lost. Step is equal to self.step. Self.step. So return loss. Return loss. And inference mode is, and then now you start at inference mode. So this puts it in inference mode because why? PyTorch, when it's on training mode, it really records every mathematical calculation that goes behind every tensor manipulation so that you can calculate the gradient descent. By adding add t.inference mode, it tells you, okay, you don't have to remember all the gradients, and this really helps in terms of GPU memories. So, PyTorch is amazing. Now, you start with evaluate the model and test it and return the accuracy, right? So accuracy is basically how many of this correct stuff divided by the total sample. So we start with the whole log, which is for batch, in tq self dot test dot loader test dot loader divided, saying evaluating. So this creates a bar progress. And then you do the usual stuff, which is, what is the tokens? The tokens is batch tokens dot to device. and then you calculate the logits. And this basically tells you that, okay, this is the format of the logits, which is a bunch of tokens. No, it's a bunch of tensor. And it is self.model, the tokens, just the tokens. Self.model tokens. And then but you don't care, you care about every batch, but you don't care about the last word of the sequence. You don't care about the last word of the sequence because the last word, you don't have to predict anything else. But that is the logits. And then the predicted tokens is equal to logits dot argmax, which is you just get the highest probability, the highest value among all the logits for the predicted token, and then -1. No, -1 dimension equals to -1. And then you want to compare the predicted tokens, the accuracy of the predicted token. So total.correct plus minus is equal to predicted tokens being equal to tokens of everything and except for the starting tokens for the batch, for that particular batch, and starting from the first unit, because you don't, the predicted token is, because for tokens it starts from index 0, 1, 2, 3. So you only care starting from index 1, because index 0, the predicted token is 1. And then sum dot item. Total samples plus minus tokens dot size 0, which is all the batch multiplied by the sequence length. This is the sequence -1. You don't care about the last word of the sequence. You don't care about the last token of the sequence. So this is it. And accuracy is equal to total correct divided by total samples. And then you log it. What do you log it? Log dictionary of variables, where accuracy is equal to accuracy. And step is equal to self.step. Do you have to add the step? Do you have to loop into the step? No, you don't have to. You don't have to. You actually don't have to. You don't have to. Self.model.train and return accuracy. So yeah, this should be correct. This should be correct. And then this trains the model self args.epochs, also 1B initialization. So that's it. This is the code. And then we are going to continue with, I'm going to start explaining what sampling is. So as you know earlier, we've just been using argmax, which is, okay, whichever of the predicted tokens has the highest value, you're just going to choose that. But this creates a problem because, for example, the sentence, the cat sat, if you just keep on choosing the highest probability, it's just going to be like the cat sat, 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 sat. So it becomes very repetitive. So there's a lot of ways to sample what the next token is. And there's methods like greedy search, top K, and advanced method like beam search of like, how do you choose the right predicted token? Is it just like the highest value? No, there's like multiple methods we can actually try. So this is implement the sample method, and I've made the code with the help, definitely with the help of AI. And I just want to start immediately explaining the different methods. So first is the greedy search, which is the most likely token as an integer, which is the same out of the logits. You look at argmax, which is the most likely token, the most likely high value, and find the item. The second time is apply temperature to scale the logits. So the logits is like a bunch of numbers, right? And if you put a temperature and you divide the temperature by a small, really small number, the difference between the highest value and the lowest value expands. And then eventually when you do the selection process, it's more clear, it's more divided, it's more different. And you're like, clearly I want to choose the highest one. If you divide the temperature, if the temperature has a large temperature, then the difference between the highest logits and maybe the second highest or even the lowest shrinks. And so the changes is much more smaller. And that gives a bit of like more uncertainty on like just rather than purely choosing the first one. And this applied temperature can be applied with other kinds of sampling method to kind of like get the answer you want. You get the answer you want. So that's mainly the job of temperature. And then apply frequency penalty. As I told you earlier, you don't want the whole token generation to be the cat sat 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 sat. So if the tokens have been created before, you really penalize like you really penalize it so that it doesn't produce the same exact token again. So that's pretty much the frequency penalty to logits. And the devocab is the entire vocabulary, right? Which is the logit size. And you make sure that the minimum length is devocab and you find out the input IDs. And logits is equal to frequency penalty multiplied by the ID of those frequent tensor, those frequent logits. So yeah, those frequent token. So now this next is sample basic. So T distribution is categorical, not categorical. Basic gives you a probability distribution. And you sample it. So you randomly choose one out of that probability distribution and you get the value. So sample top K is actually used in GPT-2. I think the number that they use was like you just choose the top 40 most likely tokens and take 10 samples out of it. First, the logits is divided into the value and the index. And so PyTorch always follow these syntax. And then you create the probability distribution again with the logits equals to top K logits, and you sample it. And after you sample it, you get the token ID. You get a token ID. So the next one is sample the P cumulative probability. So this is your input top P, which is like, okay, I just want to get the first 90% probability of the tokens. So there's just a bunch of predicted tokens, right? Predicted tokens with each with its logit score. And you're just like, nope, I just want to top 90%. So this one is like top 5, like if K is equal to 5, top P is like a cumulative probability. So again, logits that sort, you sort it from this on a descending order, starting from the biggest value to the smallest value, and then you divide it into its value and its index. You find a cumulative probability, you apply the softmax and make sure that all these logit scores squishes into probability 1. And then when you cumulative sum it of all these probability, the cumulative sum is 1. Now you go and search and sort the cumulative probability, and then the cumulative probability, and then make sure that the top P is cumulative probability, and the top P is the number that you gave. So for example, if you just want the top 90%, and the first token cat is 70%, the second token dog is 10%, the third token fish is like 5%, that the cutoff is 90%, right? So 70, 10, 15, like 85, and assuming that the next one is like 5 as well. So you want to cut off at 90. You really want to cut off at 90. So in this case, you only get the first 3 tokens. You want to cut it off in the first 3 tokens, and you add 1. You add 1 to, and this is the number of stuff you keep. And there's a minimum tokens to keep because make sure that you at least need to have 1 token because you're trying to predict the next token, right? Predict the next token. So those, in one of those edge cases where let's say you put the number 10%, and the first predicted token is like 7%, like that doesn't fill in the bar. That doesn't fill in the bar. So yeah, you get the minimum tokens to keep. So actually, that what I just said is actually completely wrong. Um, basically mint tokens to keep is to ensure the edge cases and making sure that at least there is one token that you put in and keep because you need to predict like the next token, right? And then keep IDX, you find out the indices, and then keep logits, you find out the logits of the stuff you have to keep. And then you distribute those samples again. You create a probability distribution, find out the random sample, and then tell me what is the index of this item. So yeah, that's pretty much it. Where nkeep represents the number of tokens you keep. And then there's beam search. So thank you so much, and I hope you enjoy what I just said.